Before continuing our discussion of the sensor interfacing with 8051 microcontroller, let us briefly recap some of the important terms related to ADCs. The first most important term is resolution of an ADC. What exactly do we mean when we say a particular ADC is having an n-bit resolution? It actually means that how many binary digits or bits are used to represent the input signal, input analog signal that is to be converted or that's to be digitized. So basically we might have an ADC, there's an input that is an analog signal and the output is a digital signal. So this ADC can have a resolution of 2 bits, that's every input voltage will be represented using 2 bits, or it may also have a resolution of 4 bits. That means every input voltage will be represented using 4 bits. And similarly ADCs can have 8-bit resolution, they can have 10-bit resolution, they can have 12-bit resolution, and they can have 24-bit resolution. More the resolution, more will be number of states, number of distinct states. For example, if number of bits is only 2, then we can have only 2 raised power 2, that is 4 different states. And if we are having a 8-bit resolution ADC, then the number of different states will be 2 raised power 8 equal to 256 different states. And more the number of different states, less will be the step size. Step size is the second most important term related to ADCs. What exactly is step size? Step size is actually smallest change that can be recognized by ADC. Let me give an example. We have an ADC and we have an input voltage that ranges from 0 volts to 5 volts. And the ADC is 1-bit resolution ADC. That means there is only one output. So there can be only 2 distinct states, either it can be 0 or it can be 1. That means ADC has to represent this input analog voltage as this 0 to 2.5 volts using one of the states, maybe 0, and 2.5 volts to 5 volts using another state, 1. So here the step size is 2.5 volts. But if we have the same ADC, but now it is a 2-bit resolution ADC, that means the input voltage ranging from 0 to 5 volts will be representing using 2 bits. So we will be having 4 different states, 0 0 0 1 1 0 1 1. So step size will decrease. We may have 0 to 1.25 volts using one of the states, 1.25 to 2.5 as another state, 2.5 to 3.75 as another state, and 3.75 to 5 volts as another state. So basically in an 8-bit ADC, we may have 256 different states. So our step size will be equal to, if the input is 0 to 5 volts, upper value of the range minus lower value divided by number of states, 256, that is equal to 19.53 millivolts. So step size is only 19.53 millivolts. And if the ADC is of having 12-bit resolution, if the ADC has a 12-bit resolution, that means step size will be equal to 5 minus 0 divided by 4096, equal to only 1.2 millivolts. So more the resolution, less the step size. Then there is another important term that's known as conversion time. Conversion time is actually the time taken by the ADC to convert analog voltage into digital voltage. Next, we will be discussing some important pins that are associated with each ADC. So let me take an example of an ADC. We have a very basic ADC IC that comes under the name ADC 0804 IC. It's a 8-bit resolution ADC. It's a 20-pin IC. So what are the important pins present in this IC? Pin numbers, since it is an 8-bit resolution ADC, so the output will be displayed using 8 bits. So pin numbers 11, 12, 13, 14 and up to 18, 15, 16, 17, 18, 8 pins. They are the data pins, and they are usually fed to microcontroller. Output data, digital output data. Okay, there's an important pin that in this case ADC 0804, that is pin number 1, that's known as chip select. It's an active low input and it is used to activate the ADC 0804. That means to access the ADC 0804, to start the conversion, to read the data from it, chip select should always be equal to 0. That the pin must be low, the important pin. Then there are two more important pins. We have RD and we have, that's read, and we have write. RD, both of these signals are active low. So what's the purpose of read and write? First I will discuss write. It in ADC 0804, write is pin number 3. This pin number 1, this pin number 3, write. This is an active low input, and it is used to inform the ADC 0804 to start the conversion. It will also be connected to the microcontroller, and microcontroller will send a low to high pulse. Whenever the microcontroller will send a low to high pulse to this pin, ADC will start the conversion. Whatever the input data is there, it will start converting it into the digital data. A low to high pulse from the microcontroller. Then we have read. It's pin number 2. Read pin. When the ADC converts the analog input to its binary equivalent, it holds it an internal register. There's an 8-bit internal register. It may convert the input voltage, that is coming. Whenever I send a write, when I send a low to high pulse on write, it will start converting the input voltage coming here into digital data and will store that temporarily in this 8-bit internal register. Then I need to send a high to low pulse on this read signal. Whenever I will send this high to low pulse on the read signal, this 8-bit data will be transferred from this 8-bit internal register to the data pins of ADC and subsequently transferred to the microcontroller. So we discussed these 8 pins. They are for data. We discussed chip select, that is used to activate ADC and must be low, and then we also studied about read and write pins of ADC. Then we have another signal that's known as INTR. That's pin number 5, or it's also known as end of conversion signal. Whenever ADC finishes the conversion of analog signal to digital data and stores it in 8-bit register, it sends a pulse, it sends a signal, it's an active low. So normally this pin will be high, and when the conversion is finished, it goes to low to signal the microcontroller that the conversion is finished and has stored the data 8-bit in 8-bit ADC in 8-bit internal register that needs to be picked up by microcontroller. So pin number 5 is also clear. It's known as INTR, interrupt or end of conversion signal. Then we have pin number 6 and 7. They are known as V in positive and V in negative. These are actually differential analog inputs, where our V in that will be converted to the digital signal will be equal to V in positive minus V in negative. And if we have a single input, we can always connect it to V in negative to ground. That means whatever voltage comes to V in positive will actually be converted to the digital signal. Then we will discuss the power pins, which are actually used to give power to the ADC 0804. We have pin number 20, that's used at VCC, and then we have 2 ground pins, analog ground and digital ground. That will be pin number 8 as analog ground and as digital ground we have pin number 10. So then there is another pin that is known as V reference by 2. The name of the pin is V reference by 2. It is pin number 9. What is actually the job of this pin? It actually changes the reference voltage. By default, the reference voltage for ADC 0804 is 0 to 5 volts. If this pin is not connected, the reference voltage will be 0 to 5 volts. But in some cases, in some applications, we need to change this reference voltage. For example, in some cases we know that our input only changes from 0 to 4 volts. It doesn't go beyond 4 volts. Therefore, we need to change this reference voltage. We can change it by giving some voltage here. For example, if we give 2 volts, in case of ADC 0804, the reference voltage will change to 0 to 4 volts only. Similarly, if we give 1.5 volts here to pin number 9, the reference voltage will change to 0 to 3 volts only. What it does, changing the reference voltage, it actually increases the step size. Increases the step size. For the same 8-bit ADC, if the reference voltage is 0 to 5 volts, the step size will be 5 divided by 256, that is 19.53 volts. And if the reference voltage is only 0 to 4 volts, then the step size will be 4 divided by 256, that's only 15 point something volts. That is decrease the step size by changing the reference voltage. So these pins are clear. So we have discussed every pin. There are only 2 pins remaining, pin number 4 and pin number 19. Pin number 4 and pin number 19. Pin number 4 and pin number 19. They are actually used as a clock source. Pin number 4 is clock in and pin number 19 is clock R. This clock source actually decides the conversion speed of ADC. So that's it. Next we'll be writing a program. We'll be interfacing a sensor, maybe a thermistor or an LDR, to microcontroller, and in between microcontroller and thermistor there will be our ADC.